Hello everyone and welcome to Handmade Hero, the show where we code a complete game, live on stream. Today we are back. Last weekend, kind of took the weekend off. We had only one stream last weekend, and because John Blow was trolling us with Dota things on the chat, we decided to make a Dota hero generator, which actually you can now see running. I cut and paste a result from it every day. I gotta hook it up. I'm gonna hook it up to a tweet bot, but if you're interested, we've got it. It's here, and you can see that it's created some pretty high quality. It's created some pretty high quality heroes for us, with some pretty great spells. A Crockbush Shrapnel, for example, always great. Really helps with your micro. I guess I would say Proximity Crush, really really powerful for team fights, I think, if I'm not mistaken. And then who could, of course, forget Umiro, one of the most interesting heroes, our latest hero, with such wondrous abilities as Walrus Bringer, Bearer of the Demonic Restoration, and, of course, Cursed Bolt Ransack. Chemical Dream also, I don't know if he just kind of trips out or something. Point being, that is what we did last weekend, so we didn't really do any work. I mean, unless you count that as work. So this weekend we're back doing what we're supposed to be doing, which is finishing the lighting for our game system. And we're going to go ahead and get right into that today. We more or less finished the part we were working on the weekend prior, and we were ready to move on to the next part, and that next part is exactly what we want to do today. And specifically, what we were doing was fixing the light distribution. And so what we want to be able to do now is start to actually do the plumbing to get our probes into the system, draw their results so we can see whether they're actually convecting light properly. And that's pretty much all we really want to do this weekend. Once we've gotten that, then we can flip over to the GPU side of things and worry about how we're actually going to sample these things at runtime to light our entities in the world. So if I go ahead and open up our lighting system, again, remember we did the sort of basic work that we needed to do to just see that these light probes are, happening at all, right? So if we run our game, you can see this running. This is in debug mode here, so it's a little bit slow frame rate wise. But you can see that as I spin around, there's these sort of purple floating points. And those purple floating points are just the places where we've sort of provisionally have the level generator stick lighting probes. So you can see at the moment we don't stick any lighting probes out in the filler apron regions. We do put lighting probes on the interior, and we put 2 per tile. This is probably overkill, and we probably don't need to or even want to distribute them this way. And also we probably want to scatter some light probes out in the outer area as well, although probably not many, because we don't really want to spend a lot of time computing lighting in the apron, since it's just supposed to be like a dark, inaccessible area outside the sort of region the player hops around in anyway. So that's what we're working on right now, and so what I'd like to shoot for as our next goal in the lighting system, because again, lighting is very complicated. I say this very often. Lighting is very complicated, and so as a result, you want to typically break it into pieces that you can sort of independently verify are at least nominally working, if not bug-free. And so that you don't spend your time trying to just figure out where the problem is, let alone what the problem is when you have a bug. So what I want to do is I want to get us to a point where there's no GPU involvement whatsoever, other than just drawing our debug information. And I want to be able to compute these light probes, the colors of these light probes, on the various sides of the cube, and play around with that until I can look at it here and sort of at least be able to argue with a straight face that the lighting on the probe debug markers looks like some lighting you would actually expect from the placement of the lights in the world and the occluders, right? And the reason I want to do that is because until I can see that that looks okay, there's no real point in working on the GPU thing that samples them, because we would have no idea if we then just get bad results. We have no idea who's at fault. Is it the sampler that's at fault, or is it the lighting propagation that's at fault? Is it the bookkeeping that's at fault, right? And so we're trying to slice this problem up into chunks, because the smaller we can make those chunks, the easier time we will have debugging, because there's just less things we have to consider, right? And so, that's just kind of the case with things like lighting, where we don't have easy ways to like test it, or it's very hard to write like unit tests for things like lighting. I mean, the Cornell box is like the best thing we've got so far to a unit test for lighting, right? It's very hard for something that's an approximate artistic only solution. We know we're not really simulating lighting the way it works in the real world. That's way too expensive for a modern computer to contemplate in real time. And so what we're trying to do here is just say, look, because this is an artistic process, we will know visually whether it looks like a usable lighting solution. Let's try to figure out ways to bucket that up into ones we can visually verify, and then after we're done with that, we can progress to the next stage, having some confidence that the bugs in the previous stage at least aren't producing any things that will confound us, right? Okay. So what we need to do now is start to work through the plumbing of this system, and there's a couple aspects of this that we need to do. First of all, we need to actually build our table of light probes. If I'm not mistaken, right now we don't really have a way to do that. We do know that there are light probes in our system. We are ready to build a set of light probes for the lighting system to work with, but to the best of my knowledge, we never actually did any code that actually puts that light probe table to use. We just have entities that draw themselves as those little purple markers that are like, these are the light probes. And then we have a light probe system in the lighting that will iterate over them and try to move light around with them, but we don't actually plug those together. So we need to do that. We also need to actually call the function that inserts these probes into the spatial index. I don't think we did that, right? I think we wrote some code that does it, but we don't actually have any way to use it yet, right? And then third, we're going to have to build some of these additional support structures. So, for example, we've got lighting samples, right? Like this sample table of 16 light directions that we're using for lighting. Although, actually, I thought that was this, so I'm not sure what this is right now. Maybe it blows out to this. I don't really remember. It doesn't matter. Point being, we need to go back to the code that generates the directions to sample lighting-wise, and we need that to remember, for each individual lighting direction, which of the light directions corresponds, which of the sample lines corresponds to which directional contribution for a probe. And at the moment, unfortunately for us, we don't really know how we want to keep this lighting information stored, right? It's entirely possible that we would like to store it in some way other than six rough light directions, you know what I mean? And if you look, for example, the paper that I mentioned the other day, which, I'll be honest, I don't really remember where it was. Here it is. I guess I do remember where it was. So if we take a look at like the paper that I mentioned the other day that was talking about light probes, and again, light probes are a very common thing. They aren't invented by this paper. They are like old, right? Just in terms of giving you some information about how these things work, when they're used in sort of 3D, AAA sorts of games and so on, you can see here where we're talking about spherical irradiance. The question is, how do you store these things? And in terms of how they store them, I'm not sure. Let's see. Spherical distributions at discrete posts will be combined. Blah, 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 blah. Let's see. We encode the spherical irradiance. 111110 at 8 by 8 octahedral resolution. So they basically use a little 8 by 8 square that I assume just stores the color. So, I mean, it looks like then, I mean, just from looking at it, it looks like they're doing roughly what we're doing, just a little better, right? More detail, right? We're just using 6 samples. They're using 64, right? And that's understandable because they're trying to eat up GPU power, right? I mean, they're trying to make the best lighting they can. And I want to say these guys are NVIDIA, right? Yeah. Well, okay, not just NVIDIA, but at least half NVIDIA. So they're trying to, get as much power out of this as they can, and so they're probably doing, a lot more than what we would necessarily want to do. They're also targeting the very latest stuff as much as possible, right? But it looks like they're doing exactly what we're doing, so maybe that's fine. But I just wanted to give you some perspective on what some people are otherwise doing. Spherical basis functions, spherical harmonics, for example. There's just a lot of ways we could store it. That's all I wanted to say. And so I don't know if the way that we're picking is the smartest way for us. It's hard to say. And when we go to do sampling, we may find that it's too expensive to sample or it's too expensive to store or whatever. And we might want to adjust that method. So instead of using the 6 faces of a cube, maybe we want to do something smarter. Or maybe there's some way we could do something, that's going to be quicker to sample and store. So that's all I wanted to keep you aware of. But at the moment, we're going to do it that way just because it's something simple and we can visualize it easy. We can write something that just draws different colors on the side of a cube, for example, and that would give us the information that we need for determining whether our lighting seems to be working at all or not. So what I want to do now is just start on that process, which is going to be kind of slow, but we're going to go ahead and just take it slow. And the first problem that I think I would see here, one of the things that I don't super like, if you look at how these light probes are stored, we've got sort of a 6-wide piece of color information here. And what I don't super love about it is if you go look at how we actually use our hits, right? If we come in here, you can see us doing our ray intersection. And we then downshift to scalar, which we're doing primarily just because we can't do memory lookups in SIMD. It's really the sort of bane of the pre-AVX512 instruction set. It just wasn't well designed for this part of the process, unfortunately. That's neither here nor there, but point being, when we have to downshift here, you can see what we're doing. We take 4 arrays at a time, right? And we break them up into their individual single arrays. And then we do our lookups, right? We just try to figure out, where we're going to, how this transfer PPS is going to work. And you can see it accumulating that PPS in here. And this right here is the part, the sample point dir index. That point right there is just the thing that lets us know which one of these samples it should be added into. Now, the thing that I think we want to look at, though, is that when we sample a particular direction, sometimes those directions are going to be kind of, they're going to be shooting out towards the corners of the cube, right? And one question I have, and I'm not sure what the right approach is how do we actually want to record sample directions? We can just sample into the face of the cube that you left through, but it might be smarter for us to just average, like when we take, let me just draw this out here so you know what I'm talking about. So if we imagine we've got a cube, right? And we sample some direction, but that direction, like let's say we're starting from the center here, right? And that direction kind of goes off through like almost a corner of the cube. Then the question is like, you know, do we really just want to attribute to one side? If we left directly through the middle of that cube, sure. But if it's off here, or worse yet here, how come we don't add any into like these, right? And so another way we could choose to have this work is we could choose to like place this information, like distribute this information out to the sides of the cube as like a blending value, right? So we could say that, you know, this one goes, you know, 33% to this face, 33% to this face, and 33% to this face, right? Now, the reason that I find this sort of confusing is because we are also then on the back end going to blend there too, right? So when we sample on the back end and we say, okay, we have some lighting information that we generated, right? So we did all this sampling and then we produced a single cube with a color per face. You know, here's color 0, here's color 1, here's color 2 or something, right? And then we shoot a ray for sampling the light. We don't shoot the ray. We're just going to sample this lighting from this cube. If we're going towards a corner, we already do a 33% C0 plus 33% C1 plus 33% C2, right? So we're already doing that blend to produce the result from those. So we, you know, when we go to look at the lighting in that direction, that's what we get. And so the question is, what produces the best result here from this process, you know? And I really don't know. You can see the kind of problem that you get potentially with not blending. If you just use equal weighting as you kind of shoot out through this cube, then the problem is as you get towards the end, you're causing light that may be coming from over here to contribute just as highly to a sample direction that may be over here, right? And if I was to sort of draw this in 2D so it's easier for you to see what I'm talking about, let's suppose that we have a light probe, right? And here is one side of the light probe. So here's my light probe, and here's one side of it. I'm looking out this way at the very edge of this thing, right? And also out the middle. I'm sampling these rays, and I get some results. So maybe there's a red light here, there's a green light here, and there's a blue light here, right? Well, what I would like to do in the future, when I then have a surface in this area, and it's pointing this way, and I want to sample what's the lighting here, well, ideally, the best result would be for me to get heavily blue, right? Like mostly blue light, and not a lot of red light from that, right? And so if we assume that this side is sort of also hitting the blue a little bit, right? Because this blue light's over here somewhere. This is going to be blue, but this is going to be roughly white, right? So I'm going to blend a lot of white in here for that, 50% white, 50% blue for this sample, even though what I really wanted was mostly blue, right? Now, I don't know that there's that much we can really do to fix that. But again, if these things were weighted, then this would get added a lot less in there. So it would be mostly green and blue that would be added to this face and this face, right? And so when you sample that direction, you get more of it. And there'd be less light contribution from R because that would be mostly added here, right? So this would be more B, this would be more R, this would be more G, which is probably more what we want. So I really, again, I just don't really know what we want to do there. But just from looking at it, it kind of seems to me like we would rather have a blended gather as well as a blended sample, just personally. So it kind of seems like this process wants to look a little bit different. You know, it probably wants to look kind of more like this. And each one of these things, maybe this accumulated PPS, as we accumulate in here some kind of a transfer, we would want to accumulate the weights and normalize like we used to, and just weight each one of these by some kind of pre-computed probe contribution. So remember, we know like those directions that these things are going out in, and when we store those ray sample directions, what we would do is store how they get accumulated back in. So like each of these things, right, would be that way. That just seems better, right, to me. And I just think that's probably what you would want to do. So, you know, looking at this, we would sort of say, all right, there's going to be an accumulated PPS. It's going to be something like this, right? So you're going to grab that out there, and then you're going to do something like this. Just so we build that base pointer once, and then we access it off of here, right? And that way, now we have each of these sort of PPS ones is kind of off of the base one, and then we just need weighting values for these, and we're going to need to remember how much weight we did, because now we do need to sort of renormalize those values, possibly. To be honest, though, I'm not super sure how much we really need to do in terms of renormalization. It feels sort of like that's unnecessary, because, you know, we're just taking the incoming light, and so if we just always multiply by the ray weight, it should, generally speaking, just average out over time, you would think. Maybe that's not true, but it feels like it's an unnecessary step to accumulate the weighting on these things. So I might just say, let's see if we can skip it. So I'm just going to say that because I'm just not sure, and we kind of have to look at it in a little bit more detail. But anyway, assuming that we are going to do something roughly like this, what we need now is a contribution sample value. And so back here where we had sample point dir index, what I actually want there is just a blending value, right? So I really just want something that looks like this. So for each sample point in the set, I have like how it should be blended in. And when you look at these, you can see it looks like we've got sort of sets of these guys. And so what I kind of want to do is just say the sample, like this should sort of be its own bundle probably. So there should be something here like a lighting sample, light sampling sphere, something like that, right? And then these things here where we have these sample ray bits here, we'll just call these sampling spheres, and we'll make as many of these as we want. So, okay, you know, we do 16 or whatever, and that's fine. And so these are actually just 18 and 6, right? I'm sorry, 18, 6, right? So for each of these, we have for our sample point, and it's really sample direction, and that's this right here. For our sample direction, that we're heading out in. We have our like our like cube side weight, right? And so for each one of these, we want to go ahead and use the correct corresponding weight as we go. So we're just like looking up which weight we need to use here to blend this thing in, and off we go. So that's how we would update. And to get the cube side weight there, we just need to go like, okay, the cube side weight just equals whatever our sampling sphere's cube side weight was, right? And so now we can look in here where we're sort of doing these lookups like this. We can make this be based on the sample sphere now, which is better, right? So now what we do is say, all right, when we would normally go to get this dir sample index nonsense here, which, you know, is the probe index, this crap here. This, as you can see, light probe index plus sample point entropy. The sample point entropy is like a fixed value up here, right? So the light probe index plus the sample probe entropy ANDed with a sample pattern mask is actually something we can just have out here, if I'm not mistaken, right? Because nothing in here actually ever alters any of that. So what we want to do is each time through, once we compute whatever this dir sample index lookup value is, that's when we want to go get our sampling sphere, right? So that's where we want to go like, okay, sampling sphere, spheres plus dir sample index is going to be our light sampling sphere. And so we're just picking which one of these spheres we're going to use for sampling, and we can generate as many of them as we think we need to ensure a fairly random coverage. But off we go. So once we have one of those sampling spheres, we can use it for everything. So here, for example, we would do sampling sphere. And then when we want to get like our sample direction, we just use the ray index here. And this ray count, right, we need to make sure that we know that our ray count is always not as bad, right? As well, actually, you can see it right here. So we just need our ray count to always here be okay. So in here we say like, all right, we've got our sampling sphere. We need our sampling sphere's sample direction. That's going to be the ray count, because that's how many that we can pull out of that sampling sphere. And then we just send all those rays down, right? So I think that's roughly what we're talking about here. And these are constants, so they should be able to be optimized away by the compiler into just constant computations, because they don't change. They're you know, based on the structure size. So I think that's all we need to do there. And that, you know, gets us started with that bit of sampling, right? Now, we have a problem here, obviously, which is that when we are actually generating these sampling spheres, we kind of had our pattern generator here, right? And one of the things that you could see about our pattern generators is our pattern generators always generated only hemispherical patterns. And obviously, we don't want that. So if you look here where we've got our generator for 64, I guess, which I don't know why it would be generating 64 of anything, because we don't have anything of that multiple. I'm not sure what the goal was here. I don't quite know why it looks like that, to be completely honest with you. But either way, when you look at, for example, our Poisson sample generator, you can see here we're generating random bilaterals, right? And we are then looking to see whether or not we have anything in the set that's too close. And off we go. And then you can see here, like, where we are actually just, you can even see it's here, we're just using we're using sort of a method where we generate stuff on the disk, and then we loft it up into Z to generate a hemisphere, right? And again, I don't think we want to do this anymore. So I think what we want to do here is we want to just generate points that are randomly pointing in arbitrary directions. And then we want to just keep the entire sphere. So I'm going to go ahead and look here. This point where we loft them up just isn't necessary, right? So I'm going to go ahead and start to gut these routines. I don't really care about these other pattern generators here. I don't think they're actually being used anymore. They were just as when we were actually sort of playing with our different options there. I don't think we care about this anymore. I mean, I guess I could keep them, but I'm not going to bother. Well, it would be, yeah, you know what? I'm not gonna. It's just more work than it's worth. So I'm gonna go ahead and say, look, we're gonna get rid of the lighting pattern generator stuff and just simplify this code down because I want the Poisson generator pretty much period. So we're just gonna do this, and these folks are gonna go away. And then the generate Poisson samples now is, I think we can just use sort of a regular thing where we just generate samples in the cube. We'll normalize that. So then we have a, some random direction. We don't want it to be 0, 0, 0. So we probably want to avoid having it be that. One way to do that would probably be to say like this. So we'll just say, all right, we're going to keep trying to generate points. Assuming that we got one that's reasonable, we'll take p and we'll multiply it by 1 over p squared to renormalize it, right? So, we'll normalize p this way. Then we'll just check to see whether or not it's valid here. And off we will go. So, well, you know what? We were already doing that. Never mind. But I want to do this first. So I think we still, yeah, you know what? I think we still want this way. All right. So valid, we're just going to presume to be true. And then we're going to do our test over the existing points to see whether they meet the minimum distance squared that we've set up. This minimum distance squared is probably going to have to be adjusted, but that's okay. And then we record our points in here for ones that are valid. And so that's good enough for our Poisson samples. It's not a good way to generate Poisson samples, and we should probably put a to-do in here, like to-do, Casey. We could put a much more efficient Poisson noise generator in here, and probably should at some point. Because this is like the slowest possible way to do that. We would get rid of this. We don't need any of these anymore. I'm not sure. Yeah, that's probably all just fine. We don't need any of this. And then when we do our generate lighting pattern stuff, in here we can just say, we don't need any of this. We can just say, all right. We need to generate multiple ones of these, obviously. And so what we want to do here is, I don't know why. Yeah, it looks like because our generator just works in regular values and then we copy them out. So what we want to do here is say, I don't know that we really need to do bundling of rays and some reductions, but maybe we do. That would potentially speed things up since we cast multiple rays at a time. If we always cast, like, you know, the rays that go out one side of the cube, we probably could avoid... we could probably process things quicker because we wouldn't have rays falling out of the active set and stuff as soon, because they'd probably tend to hit similar things at similar distances if they go in the same direction most of the time. So this to-do should probably stay. But either way, as we go through this version index thing, what we really need to do here is just grab our sampling sphere now. So this is getting whichever one we're working on right now. And then this code stays basically the same. So we come through here and we basically build, you know, this dest up. But what we don't have yet is we want this cube side weight here as we go through our direction index, right? We want our... well, interestingly, if that's going to be 18, though, I'm not sure how we picked that. But this generator here needs to generate, like, enough to fill this sampling set, right? Just looking at this. So 4 times dir index, whatever this sample direction here is, right, needs to ensure that this has enough of it. And at the moment, it doesn't actually, right? Because if it was 18, 18 times 4 is going to be more than 64, which means it would require more than what we've got in this array for sampling. So that seems like a bit of an issue, and I don't know exactly how we want to do that. You look at how the point count works out here, and I mean, I could just say, but you do have a problem, which is like this value. We don't know what this should be. Like if you want to insert, you know, 300 points, then their minimum distance has to be smaller than if you were only going to insert 64 points, right? So that value we would have to adjust as well. And again, one thing we could do is we could just spam that many points out randomly onto the sphere and then use some kind of iterative repulsion to like push them to whatever their natural distance is. And that's totally fine too. And that might be something we want to do because, again, we can pre-compute all of these. And furthermore, I think there's some other stuff that we probably want to do here. Like, probably what we want to do, since we know we're iterating over these sample directions, is we probably want to produce a blue noise pattern over the sphere that is the complete set of blue noise samples. And then each one of our sampling spheres that we take is a slice through there that picks like the set of points that would be in the remaining set and that are all as far away from each other as possible. You know what I'm saying? So that basically we maximize on any given frame. On any given frame, we are always sending out a set of well-distributed rays. But also, across frames, we are also distributing, so we're not like casting in the same direction as we casted on the previous frame. You know what I'm saying? And as I'm saying all of this, it's making me just want to just do this correctly the first time. And so I think I will. I think that's exactly what I want to do. And so what I think I'm going to do is just, we're going to make a little generator, I think is what I'd like. So like, for example, I'm going to go into Handmade code. And we have like our little utilities and whatever. So I'm going to make hhsphere.cpp. And we're going to just do this inside there. And we're just going to generate these things as a totally separate pass on the system that you can then just like load in and use, right? As just like an include file. So what I want to do here is like have a pound include that's something like handmade sampling spheres.inl. And that handmade sampling spheres.inl would just be like the directions that we've, effectively pre-computed, right? And in there, furthermore, what I would like is actually, I kind of want that to be put like maybe right here even. And so that it's got the information there. But then that will define the rest of our stuff. So in light sampling sphere here, when we're talking about like how many things there are and all that sort of stuff, maybe that information is actually encoded into that INL, right? So like this structure here with the sample direction and the cube side weight, like maybe those are actually defined inside handmade sampling spheres. And that way, when we change how we build the sampling spheres, this code automatically adjusts how many rays it thinks it needs or has or wants or whatever else, right? And similarly in here where we've got light sampling sphere, that maybe is just that. And then maybe there's a pound define that's like, You know what I'm saying to you? And so then that value, whatever this value ends up being, can be generated as well. And then anyone in here who is doing like an array count on the sampling spheres here is not going to do that anymore. So can't see anything because my head's in the way. So that, for example, this right here is actually just going to be, oops, no, that's not one. I take it back. Well, there must be somebody because there's that mod of it, right? Huh. In Raycast, it should have done one. I mean, not in Raycast. Right here, it should have done one. So it's this right here, right? And so that thing needs to be this. All right. So that's fine. And what we want to do now is have this handmade sampling spheres.inl. We want this to have this piece of information in it, right? That's what I wanted to do. And so we would have like a handmade sphere thing. It'll generate these out, and that'll be our sample table that we use at runtime for the sampling. If I go ahead and cut this out and actually make one of these, then we can just sort of imagine what this should look like. It should have these two things in it. It should have one of these structs. And then it should have like the set of light sample spheres. So it should have something like this. And so in here we've got our sample directions. And then we've got our cube weights. The sample directions, we need 18 of them. They're v3 4x's. So they look like this. So that means we've got, 3 things of 4 things, right? So we've got 4 wide x's, 4 wide y's, 4 wide z's for the v3, if that makes sense. And then we've got 18 of those, right? So if we were to break this apart, we'd want 18 of these, and then inside here we would have 18 by 6. Right? And that would close off. I think that's all we really need, and then we have that many of those sampling spheres. So I think that's what I want. And if we contemplate having this, I can now, because we've got one now, right? I can go ahead and make this thing like so. I can go ahead and fix my compile bugs and get it actually compiling, right? And make sure that that's all going to be fine, which I assume it is. So in the cube side weight for the sampling sphere, so the way that this is indexed is each ray is shooting out one of these things. So for each ray and then subray, we have to know what the weight is for that thing, right? So in here, we're probably down. Yeah, so this is not, it's not quite gonna cut it, right? So for each of these things, for every sample direction that we have here, so however many this number is here, we've got 18 sample directions, but they're 4 wide. So really we have 4 times 18 sample directions, which means that we need 4 times 18 cube side weight, right? So you need that, right? Because for every one of those that you grab, you need to actually grab 4 of them. So in here, where you do like cube side weight, you would have to say, all right, the sampling sphere, we want to take the cube side weight and we want to move it forwards by 4 times the 4 times the ray index plus the subray, right? To get to the right one, which ray we're talking about here, and then we can use the cube side weight from there, which isn't great, right? But I think that's what we actually need. And for the cube side weight, this doesn't have to be a plus anymore. I mean, it's this. We're actually looking it up and getting back an array of 6, so that's actually a dereference. For pattern name, we don't need. We're not going to do that anymore. We're just going to generate these offline. And the generate lighting pattern call doesn't really need to be there anymore. All we really need to do is say that our sampling spheres just plugs into this, right? Because that's going to be like something that we output from our routine. So I think that's what we actually want to do. And now I can go create that sampling spheres lookup table. And what I'd like to do now is just have a way of visualizing it so I can see whether I think our sampling spheres are any good. So if we look here at our startup, what I want is show me the sampling sphere. And we did some code for this. I don't know if it still works because it's like old. We had sort of had some code that would just draw the sampling sphere, and I don't actually know if that's still in here anywhere, right? It might be, it might not be. Let me take a look. So if it was in here, it would be drawing the debug lines, right? And I don't know if that's anywhere in here. This is... So we have things that draw our debug lines, and that's all fine, but we don't actually have anything that outputs the debug lines from our sample spheres. So I guess what I would say is we just need something that will do that, and presumably that wouldn't be too hard. As far as whether the debug lines are on or off, we probably just need to hard code that to on for now. So, you know. Oops. Yeah, I think what I'd do here is say, look, let's turn debug lines on just permanently for right now. And then I'm just going to have something that pushes those debug lines on there. In fact, this looks like the code we want, right? Basically. Wait, why is this doing a push cube? I don't know what that code's still doing in here. So this actually looks, so push line segment. It looks like we weren't using debug lines. It looks like we were just using push line segment. So it looks like we do actually have the code that we need here, right? I mean, this is all that code. You can sort of see it. So I think we can just use it. I think this is exactly what we want right here. We don't need this stuff. I'm not sure why we have any of this still in here. This is not going to ever be useful for anyone. Yeah, so you can see both of these. Here's one that draws them with little cubes. Here's one that draws them with little line segments. I don't know which one we want. But probably doesn't much matter. So in here, I'm going to do point index here. We're going to take one of these lighting spheres. We'll just take a look at the first one at the moment, but we may want to wrap this in a for-i loop pretty soon. We're then going to go here and say, all right, let's make sure it knows that we're going to draw 6 of these quads for however many total rays there are. While we're in here, I'm going to do like sampling total rays per sphere. And I'm just going to say that we're going to have like pound defines that so that we can look up all of the information that we want. So in here, we're going to have like a light sampling ray bundles per sphere. And total rays per sphere, this is going to be 18. Right? And this is going to be like 4 times 18. Or 4 times this. And that way you can just know what these are. So if I want the total rays for a sphere, I'm just going to say that. So we're going to say, look, we're going to output this many cubes. There's 6 faces of a cube, and we know we want light sampling total rays worth of them. We're going to go through and draw for each one of the sample points, which again is the number of bundles, because we do 4 per. And then we're going to extract just the components there. We're going to use our debug color table here, it looks like. Probably. I don't really know if I actually want that color table. So for the moment, I think I might actually just do this. But we can do that later. For some reason, I actually want that. And then in here, we'll do, for our normal, we're going to get the component out of the sampling sphere. So here's our sample direction 0. Sorry, point index. And then we're going to get the comp index out of it. We're then going to push the cube on there. This start point, I don't know where that came from or what that's supposed to be or why, but it looks like it was just set to be a little bit off the ground, which is probably fine. I'm going to go ahead and compile this. And what we should see is nothing, really, because we just got garbage in there for now. But then I want to go generate some points and see if we can get them being displayed. So get current quads takes what? It takes the render group, the quad count, and the renderer texture. In this case, it's just the white texture, because we don't want to put any textures on these things. Push cube. Actually, why do we even need this? I don't think we do. Push cube. Yeah, push cube will just do what we need it to do. So I think this is just code from long ago. Just hasn't been updated ever since. We can just have the push cube do that. Yeah. So that's the starting location. The radius of the thing is just going to be this. I don't know what else we need there, but probably nothing. And now we should, well, we're not really going to see much, but what I can do temporarily to get this working, you can see it, it's right there, right? So I think what I'm going to do is just go ahead and write that generator, load it in here, and let it look, let it look like it looks. All right. So if I go ahead and load up HH sphere, which is this code, I know now what I want it to generate, which is this code, right? And so all I need to do here is just actually make something that will output this file exactly this way. So I'm going to make like a output blah function here temporarily, and I'm just going to make this thing print this stuff out. Something like this. And so in here, we know we want this, right? So we pretty much know that this has to be a power of 2, right? Our array bundles per sphere is like whatever we want. And then this stuff is actually just rote because it's sort of calculated right there, right? So we'll print out all that. Looking at this, it turns out this is actually fine. And we really don't actually need it to be in there. But because we're just defining everything in that file, I think I'm going to go ahead and keep doing that because it'll just make it a little bit easier and it won't create like a tangle of includes. It'll just like have it in the correct place and be done with it, right? But you can see that it's actually rote. Now that it's based entirely on those pound defines, you don't actually need the generator to actually change the nature of the structure at all. But, Okay. So that's like the preamble. And now we get to the actual part that we care about. Which is this table. And we need 18 of these guys, right? So we just need this to be inside a for I loop that we're going to print out. Like so. And then we need to do the same thing. So this is like what we were estimating there. And so this is 4 times 18 of these, right? So we just need to print out lots of those. This opening, so just looking at how this goes. I think we need an extra bracket set here though, right? So when we say 18 of these, we mean 18 sets of 3. Right? So this is correct, but this bracket should actually be holding, it should be one more bracket level, I think. Right? I think it's that. And then you close that bracket and open another one for these guys. And then you close that bracket, and then you close these 2 brackets. Oops. And just again, looking at this, so you're saying like, look, we're making one array of light sampling spheres, which is this first bracket here. For each light sampling sphere that we want to do, there is a bracket, so it's this. And since we know we want multiple of these, we're actually going to put this whole thing inside a for I loop eventually, right? That's going to happen like this. So each one of these is a light sampling sphere. Each one of these right here. This is the array of sample directions, and this is the array of cube side weights, right? And so here, for example, where we look at these, that's going to be this way, but this is actually going to look like that. That's my argument. I'm sticking with it for now. The compiler will tell us if we're wrong. Know what I'm saying? But I think that's roughly what we're looking at. And so what we need to do here is we need to pass some information to this thing, just some basics, right? We need to know what the light sampling sphere count is. We need to know what the ray bundles per sphere is, right? And then when we come down here, we need to loop over those things. So the light sampling sphere count, for example, we're going to print out that many spheres. For each of these, we need to know how many ray bundles there are. So that's printing these out, right? And then finally down here, we need to print out 4 times the ray bundle amount, which again is computable by us. So we might as well just do this. Right? And that's for our like cubes or our weight index. And so we print out one of those for each one of the bundles for now. And again, that's the only part that I really don't like so far about what we're doing. I don't like how much bookkeeping is required in like the spheres. And I think that that's where something like spherical harmonics actually works nicely is because you just have some coefficients and you don't really have to think too hard about what those coefficients mean during most computations. You can just kind of store your stuff in there. That just is kind of a nicer way to think about things sometimes. So, you know, I don't like having to store all these, like, you know, I would rather have something that you could just somehow use those normal directions just directly. And that's something that, you know, I'm just red flagging, right? I'm just saying, like, you know, hey, watch out. This looks wrong, right? So anyway, moving on, what I want to do now is I want to output this sphere INL like this, and I just want to have some place set it's going to go, and I'm going to pass it this information, which I think is the only pieces of information it actually needs. So I mean, who knows what we're going to do, how many of these we're going to do. For right now, let's just say it's 16 and 18, because I think that's what we had in our thing before, but it don't matter now because we should be able to just like set these with abandon, and we should be able to make our stuff work either way, right? So when we do our output sphere INL, we need to pass those two things in, and then we also need like this file, like where's this crap gonna actually go? So that'll be like the output of our thing. So let's do that. And so in here, we need some way of saying like what the thing is that we're going to try and output. In this case, I'll just read that from arg. So I'll say like, you know, maybe the arg count is just a thing that tells you maybe exactly this information. So maybe you need like 3 arguments to it: the sampling sphere count, the bundles per sphere, and then just where to write the thing. So if that was the case, we would need our arg count to be 4, right? And otherwise, we'd like say, hey man, it's not gonna work. Something like this. You know what I'm saying to you? And so when we print out that usage information, we just expect the person's going to be able to put it in exactly that way, so that then when we come through here, when we create these things, we would say something like this. You know what I mean? Wow, that's some good spelling today. And I think that's all we really care about here. And then we can just report an error if we can't get that for some reason. But this would basically be the entirety of the function. And then we just need to write the generator the way we want to write it. And this, in theory, would write it out for us. So let's start by kind of like working our way towards getting this compiling. If I go look at... one of these guys, if I just bulk import everything, well, we don't need Windows. But if I bulk import everything else, and I just go down here and we look at, let's say 1, one of these things, right? So in here, we want to compile our sampling generator. We can do our compile. It's called hhsphere, and that's it. In theory, that should now get compiled. If we look in here, it can't find the random series. So, you know, I guess we would just need handmade random. And it's handmade SIMD, right? Yeah. Which we would have needed anyway. Looks like there isn't one of these. So compiling that, if we then look here, you know, this has some residual in there. We don't care about that just quite yet. So I'm going to go ahead and nerf that out. But now we should get our, we should get our sphere generator, you know, doing its little thing. And if we go actually invoke it now, we should be able to start like debugging that and getting our sphere include file written. To do that, we could just go to the temp directory, build hhsphere.exe. It should tell us this, right? Because we didn't give it any parameters. If we say we want 16 spheres and 18 ray bundles, and we say that it goes to handmade sphere.inl or something like this, then it should generate that file for us. And there it is. So we now have it outputting something. Who knows if that something is correct? It looks like we forgot to indent some of our lines there, but that's okay. And this is basically just a giant data table, right? It doesn't do anything else. But it looks like it put out everything correctly. Like there's the count and the mask, and off we go. And that should be ready to pound include. So now what we want to do is fill it out with some actual data, try including it, and see what happens. If I want to, I can roll that into the build process as well, which I probably do want to do, but one step at a time. So here's our generate lighting pattern call. Our generate lighting pattern call wants to have some way, you know, of storing the stuff that it creates, right? So you can see it creating like temp stuff here, but we need it to actually create real stuff. So we need it to call generate Poisson samples like this. And we need it to actually put them somewhere after it's done. We know that this temp storage here, for example, we actually need that to be a certain size, because once we get told how many light sampling spheres there are and how many ray bundles per sphere there are, we need to start like working with that. So if we assume that in here, when we do generate lighting pattern, that someone's going to tell us like this, right? Then what we need to do is we need to make sure that in here we have 4 times the ray bundles per sphere as storage space that we can use to like output this data. And furthermore, we need to like, that's like just some temp information, right? We need to do that for each of these. So as we go through here and do, you know, that as well, as we go through the light sampling sphere count, we need to work with these things together. Now, what I'm suggesting, and I think this is a good idea, but maybe it's dumb, I just think it's a good idea. What I'm suggesting is I want to change up the way that we were creating these. So before, we were creating each sphere separately. So we don't consider the spheres together. We consider them as discrete units, and we go from there. But what I'd much rather do, is take and cover the sphere with densely sampled points, densely sampled blue noise, and then extract slices from it that are all sort of uniformly distributed to some sense, to some degree. Now, we know how to do this in a variety of ways. The only thing I'm not sure about is the slicing, right? Because what I want to do is take a blue noise sphere and break it in, then pull it apart into a number of spheres that combine back to the original sphere, each one of which is roughly blue noise shaped. And I think the way you could do that is just by always picking the furthest point or something, which is n squared e to a certain extent. The naive way, meaning if we literally didn't classify the points at all and just every pick of a point looked for the furthest point away, that might be prohibitively slow. Or it might not be. I mean, as you crank these numbers, it might be, but we know they can't be that high to begin with because the ray bundles for a sphere has to be pretty low. And how many of them do we really need at the end of the day? So, I don't know. We'll see. I'll start with a naive solution. We'll see how it goes. So, let's start with white noise and go from there. What I want to do first is allocate some space. So, I'm just going to say, okay, we've got our vertex storage. So, these are our directions, all of them. And I want to make a total ray count, right? So, total direction count is going to be however many spheres we have times however many bundles we have times 4, right? And then what I'm going to do is allocate space for exactly that many. I'm then just going to loop over each of them. And I'm going to just set each direction completely randomly first, right? So in order to do that, I'm going to do just a standard thing you've seen me do multiple times before. It's just, hey, create 3 bilaterals. That gives me a white noise to a certain extent, to the extent that our random number generator isn't busted. It gives me white noise inside a cube. I can then normalize that. And I can keep it if it actually the only time that would fail is if it was 0, 0, 0, right? Otherwise, it will always produce some direction. And so all I really need to do is just guard against that one specific case, and otherwise my white noise is fine. So if here I do total direction count, maybe I'll do this. Or this. We'll just go through here and say, okay. Actually, you know what? No, I'm not going to do that. I'm just going to do this. Okay. We'll go through and say, okay, if length squared dir is greater than, or is greater than anything, because it's been normalized. So if it just didn't come out to be 0, then we increment. Otherwise, we don't. Right? So we're just going to go through here, seed the white noise out first. And then what we're going to do is for each sphere, we're going to extract points from here into the spheres. So what I'll probably do is have another thing that we create here that's something like, was this point used in a sphere yet or not? And what I'll do there is say, okay, oh, and I can use my own because I forgot we've got our types in here. All right, so I'm going to go ahead and allocate another array here, which is just one of these things, right? And so I'm going to allocate all of those, and each one of these as we go, I'm also going to say like, oh, okay. Oh, you know what I forgot to do here? Forgot to actually record this. try to avoid error here by doing this. So that will initialize a table all to false, saying we haven't used any of these yet, and it will initialize all of the directions to white noise, pointing in random white noise directions on the sphere, right? And they're not really white noise on the sphere because it's a cube that's been projected to a sphere, so it's really white noise in a cube projected to a sphere, which is not the same thing. It doesn't matter because we don't want white noise anyway, so we don't really care what our initial seed is because we're going to be cleaning that up and doing different things with it. So, we can kind of ignore that for now. We then have to go through and create our individual spheres. So now we have our, sphere index equals 0, sphere less than light sampling sphere count. And now for each sphere, we need to pull out enough vertices. So we need to pull out, like we would right here. So here in our sphere index, as we go through, what we want to be able to do is pull out the exact number of directions that we expect to have, which is this. Right? So what we want to do is, and I'm going to call this bundle index because it's not a direction index, it's a bundle. It's 4 directions at once. So for each of these, I'm going to say, okay, there's a bundle index. Like so. And then what we need to do is transform this into something that's going to pick these in an actual intelligent way. Now, the first thing I'm going to do is to just take them randomly, and that way we can just get a white noise, n spheres, all of them white noise. Again, it's cubic white noise projected, so it's not white noise on the sphere, but it's similar. It's related to that by a projection function. Just get that drawing and in the game, and then we have to come back here and start to actually make this do something intelligent to produce good noise that we actually want, sliced in a way that we actually want. So going through each of these, what I need to do is, first of all, have some place that these are stored. And so that is something that I guess we would expect this to probably pass in. And so I don't know how we actually want to store this. That's kind of a good question. But I guess what I'd probably say is we might just want to do a thing here where we have something like this. And in here, we're going to want to store the component information. Now, we don't need any of this stuff because we're just printing these things out. So we can actually not bother, now that I look at it, I'm like, we don't really need to store them in actual v34x's. We can, but we don't actually have to for any real reason, right? There's no actual reason that we need to do that. So instead what we could do is store them as something else. I don't know how I feel about that either way. I suppose what we probably want to do is just do it like this. And say, all right, we've got this, we know this is what we want to actually print out. And so what we're going to do is store like or maybe just that. Something like this. And then these here, right, we know how many there are supposed to be, so we'd just be doing this. Right? And so maybe this is just something that gets passed in. And that way, in here, when we write this stuff out, we just write it out, right? And so here in our sphere stores, we can just go for each sphere. And that plucks out each individual sphere store that we want. We then go through here and fill out that thing. And we can do that by just writing to the sample direction and writing to the weights. So here we would say sphere sample direction bundle index. And this can stay the same. It would not be temp, though. We would actually want to have like 4 things that we actually grabbed here, right? So we would want to take these directions here and actually get them somehow. Now, for now, I won't bother actually doing that, but we'll want to do that in the future, right? But it would look like this, where we grab these things out, 4 at a time. And furthermore, we would want to advance by the sphere amount inside the direction. So we'd probably, for now, also want to do like this. Right? Now, again, that's kind of stupid because, even at first, we probably want to go ahead and just simplify that just so it's a little easier on the eyes. So we'd probably do something more like this. We'd load up a particular direction that we're getting our V3 out of, right? And then each one through here, we'd just probably do something like this. Right, and again, we don't really care what's going on here. It doesn't really matter, but it'd be something along those lines. Furthermore, in here, for the weights, we know that we need 6 of those as well. At the moment, we don't know what they are, so we would just do something like this. Again, all good. Nothing particularly weird happening here. So I think that's mostly what we want. I will probably just put nonsense into our random seed for now. And I think we're good to go. So I think that roughly does what we want. And so now we just have to fill out the rest of the program to print it. And I think that'll even leave us a little time today to start playing with this. But then tomorrow we can pick it up and actually produce some good sampling spheres for us to use that fit the nice sampling criteria that we would hope for. So in here, if we've got our sphere store, I'm going to go ahead and just pass that along. So in here, I'm just going to say, all right. When we output this stuff, we're going to output our sphere store. And then in here, I'm going to actually allocate this sphere store and the storage for it into the system. So the first thing we need to add is, for these spheres, we need to print them out sensibly. So we've got the loop over all the spheres needs to pluck out which sphere we're actually talking about. We then need to go over each ray bundle for the sphere and pluck that out. So that's a V3-4X. And that's just the sphere sample direction. I don't know what we called that up here, sample direction. Ray bundle index. That gives us out the one we wanted to print. And so then we just need to actually print it using a bunch of crappy %fs, like so. Right? And I don't know how we want to do this. We could actually write a for loop. It might not really be worth it. But once we get the bundle, and we don't really need an adversor there. Once we get the bundle, we can just pull out the ones that we want. So I think in this case, where we've got our SIMD code here, if you look at how V3-4X works, you can see that we've got an E. That E picks out which one of the 3 you're looking for. So we would basically say, okay, we're printing the first one now. Then inside there, You've got an E which says which member, right? And so that we would look like that. Again, it's just this the whole way, right? So I don't think I'm going to bother with a for loop. It's just more typing than it's worth because C is too friggin' verbose all the time. But still not particularly difficult. And that should be fine. That prints out the ray directions as V34Xs that can then get loaded back in, hopefully, as M128s. Later on in the process, in here, where we have our weight bundle index, that needs to get printed out in exactly the same way. So we've got our cube store, cube. That's going to be sphere cube weights, or just weights, I think we called it. Weight bundle index. And then in here, again, it's just looking up the elements of that cube that we print out one at a time. Again, don't really need that. And so in here, we've just got our 5, 4, 3, 2, 1 weights. And then I think that prints everything out that it should, right? And so now all I have to do is allocate some space for that and actually call the functions. We don't currently call the generator. We're going to have to. So here's that, right? Let's go ahead and call it. We know the light sampling counts like so, and we'll have our spheres there. First thing I need to do is allocate space to store the spheres. In order to do that, I have to allocate space for the number of spheres we expect to have. Right? Oops. And then I need to allocate space. Why is it's having some trouble with that? And then I need to loop over each sphere and allocate space for the things that the sphere needs to store, right? So for each sphere, we just need 2 arrays. We need a sampling direction. And we need our weights. Again, each of these is a pretty simple malloc. In this case, we're looking at ray bundles per sphere times the size of each individual bundle. And in the weights case, we're looking at the number of bundles, period. Sorry, the number of bundles times the number of rays per bundle. Right? Then when we do our output sphere, I just need to pass this along. And now I think this is ready to run. I do think, so in our cube, for each bundle, you can see this is actually not right then because the weights, we need to write out more than that number of weights, right? So for here, we need to, for each one of the directions that we actually picked up in there, like, I don't know, whichever you want to call it. I don't want to call it a slice index, but like, something like that. So for each bundle component, we actually need to compute this. Because remember, there's one of these for every ray, and there are 4 rays per sample direction bundle. I think that's it now. So running this, we're going to have to debug now. And so what I would like to do is maybe sick remedy on it so I can step through it and see what's up. In order to do that, I'm just going to go ahead and call remedy on it like so. And in here, I noticed, by the way, I don't think this is our fault. It might be. Let me just double check first before I ask. Yeah, I wanted to mention that it looks like Remedy no longer can take stuff from the command line for some reason. And I don't know if maybe that's because I don't know the arguments. But George, are you with us today? I don't know if George is here. I was wondering if there was a way to get Remedy to take that. And it might be that there's special flags now. Because Remedy has a bunch of command line options. So it probably is no longer sufficient to just pass that. But I'm curious what you do pass. Maybe it's in the docs. I don't know. But just something to think about or to tell me about. Maybe put it in quotes, or maybe it just can't do that. Like have the arguments get passed. You know what I'm saying to you? So it looks like it just can't handle arguments at the moment, right? So yeah, it would be cool because I'm 99% positive that that used to work. So I think it might just have been a regression because Remedy gained a bunch of powerful command line features. Actually, you can see you can like drive it, you can add and remove breakpoints and stuff from the command line for like a running instance. So all this stuff is like pretty cool. And probably what happened is when that went in, the command line parsing had to get a little bit more fancy. And so it probably doesn't work with the old thing anymore. Just for reference, you might need a command because it might not be obvious like how to like if you just send that crap down, it might not be obvious to Remedy what's going on. I mean, maybe you could just say if I don't see a command as the first thing, then the rest of the things are arguments. I don't know, but something to think about. Because it would be fine as well if you just did, you know, that or something, right? Or, you know, it doesn't really need to do anything specific. But I just thought I'd mention it because I did notice that the other day. It's something I rarely do, but it does seem like it has trouble sometimes with that. All right, but I don't care about any of that right now because again, not really a problem. It takes like 10 seconds to just put it in here. But it was just a feature that Remedy did have, so I figured we might as well report it to get re-added. All right, so here in the settings, I'm just asking it to do, in the temp directory, I'm asking it to output that handmadesphere.inl. I'm going to start stepping in, and you can see it running here. Just going to make sure that it actually gets the information that we think it does, but we kind of already know that that was working. Oops. Light sampling sphere count and array bundles per sphere. So these are the numbers we expected to get. We're going to allocate our information here and then start to generate the pattern. So now we should have spheres that kind of go out to the correct number. So like, for example, sphere 15 should actually have you know, space reserved for stuff, and it appears to. But sphere 16 should not. Although it might point to stuff anyway if it's just in that page. So it's hard to tell. Yeah, there we go. So sphere 16 doesn't. So that's nice. So then we could kind of come out here and say, all right, let's look at generate lighting pattern. That's going to malloc some temp storage for the directions. It's going to populate that. Let's take a look at what it wrote. Oops. Again, totally fine. If I look at this as like a sort of an array of stuff, what I should see now is when we come around, we'll populate the next one, and we do. Populate the next one, and we do. So, you know, that's all fine. The total direction count in this case should be 16 times 18 times 4. And that looks about right. Yep. And so that should just populate our entire array. And then when we go to print it out, I didn't actually step through that code, but in theory, it should just print out all of those values. Let's take a look and see if it did. If I go in here to forcoder, I'm going to close this out because I don't need it. And I'm going to load out of the temp directory that INL file. They probably should have Fs after them so the compiler doesn't complain. But, you know, that looks about right. You know, I mean, who's to say, but sure, right? So I think we're roughly generating the correct stuff now, and I just need to put some Fs in the printout routine. But other than that, I think we're ready to go. And we're just about at the end of the session anyway, so that's a good time to wrap that up. But let's see if we can't just load these into our renderer test, draw them, and verify that we've actually generated some spheres for sampling. So in HH sphere, if we look at our printouts, really what we need is just these things have to be %FFs. So really all I'm doing is like replacing %F with %FF, just to stick the F at the end of it, right? Just pretty basic. That's all I really need to do there. And if we, if we were to add this in now to the Handmade Hero build process, I should be able to use that INL file, right? I do want to save this to our debug directory as hhsphere.rdgb. That way, when we need to debug it, we can switch quickly using this menu, which I like. So if we run Handmade Hero now, we shouldn't see anything different because we're using the same INL files we were using before, which doesn't have anything in it. But what I'd like to do now is replace that INL file with one that we've generated. In order to do that, I'm just going to, for now, use the command line because I want to play around with it a little bit more. So what I'm going to do here is I'm going to run this command, and I'm just going to have it overwrite our file. So basically, the w handmade code handmade sampling spheres.inl, that will overwrite it. And so now if I actually build, we should be including it. And so you can see we've got a compile error there. Oops, this is old news. There we go. It's telling me I have too many initializers. But who is that actually referring to? In 8,11. Too many initializers. But this is a struct? What is it talking about? I don't follow. Is it just reporting that error weirdly or something? Because why would it be complaining about too many initializers in something that isn't an initialization? If it was complaining down here, that's what we would expect, but it doesn't look like it is. I'm going to build from the command line just to double check. Because it looks like it's only complaining about it on that line. And I have no idea what that is complaining about. Light sampling array bundles per sphere. I mean, that should just be an 18, right? In other words, we're just talking about that. I don't get it. Okay. So I guess my first question is this just the compiler outputting a really busted error? So for example, if I was to get rid of the actual initializers in the file, like so, does the error go away? It does. So it seems like it's trying to tell me that there are too many initializers in here, and it just got really confused about how to do that, I guess. I'm not sure. So let's go ahead and put these back in and see if we can figure out exactly where it's complaining. So we know that we need n of these sampling directions. So for light sampling spheres, let's look at what we've got. This outer bracket here is the sampling sphere, contains the sampling sphere. This contains the sample directions. So for each sample direction, we would expect to see 18 V34Xs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we do see exactly 18. Let's see if these look reasonable, because we don't know, maybe these themselves are busted. So in this case, we've got 1, 2, 3. Each one has 4 things in it. So that all seems good. I'm wondering if maybe the problem is that because it's a union, it's having trouble with that. And I could see that because, oops, let me just jump to V34X here. I could see that because it probably doesn't know how to initialize that properly for the V34X E values there. Like maybe it's just confused what it should do. And I don't know. This is always the problem with C++ nonsense. You just want to say, I'm trying to input this data and I want you to build it into this type, please. Just do it. But that's always easier said than done. I think that's probably what we're seeing here. I couldn't say for sure, but that's my guess. And in order to test that guess, I guess I'll just do this. Because that's essentially what we have here. And so if I took out the unionness of this and just changed it to that, I'm wondering if now we still get the same error or not. And let's look. So here we're still getting too many initializers. That's actually reassuring, because if that's actually the case, that means it's not the union, it's just something else. So let's take a look at what actually is happening there. For the light sampling sphere, we have 4 things. That's our guess, right? We have 3 things here. If I put a comma in there, even though you don't really need one. I have 3 things inside this, so that's our guess, our outer guess, right? And then I need 18 of those, which is what this looks like. Again, not really seeing where the problem is. It would be really helpful if the compiler actually output a useful error for us, but it's really adamant about not doing that, and I don't know why. So I'm going to keep going down this road. I'm going to go ahead and clip out everything else. So now we're just working with this, and I'm going to eliminate all of these. So we're just going to see if we can get it to do one thing. Right? So again, here's our light sampling sphere. because this is an array of light sampling spheres. So this is the light sampling sphere. This is our guess, right? No, sorry. This is our sample direction. We need 18 of them, or no more than 18 of them. This is our guess. And this is our guess too. So what am I missing, folks? What's the problem? That looks totally correct, right? I mean, isn't that exactly what we said we had? I guess I'll start small. Is this a guess too? Do you think that's a guess too? You let me know, compiler, because I have no idea. There. Do you think that is, or don't you? So it thinks that's a guess. It thought that was fine, right? It thought that was totally fine. Didn't have any problem with that. Okay, so now let's try a guess. A guess needs to have 3 of these, right? So it should look like this. So it doesn't think that should be happening. Right? It doesn't like that. It says there's too many initializers. And here it's actually able, for whatever reason, it's actually able to report the error in what looks like more the correct spot, right? It's actually at least flagging this, which is something. So here's our random test. It should have 3 guess 2's in it. Here's 1 of them. Here's 2 of them. Here's 3 of them. Where is the too many initializers? Where? Do you guys see it? Because I don't see it. If I double bracket it, but you shouldn't have to do that. Because we didn't have to do that before, right? But it looks like it wants that extra bracket. But before it was an array and we didn't put the bracket in, right? So, I mean, in other words, if you don't put a bracket there, which you don't, why do you put a bracket here? It's totally wrong. Like, these are both exactly the same thing. And yet, for some reason, this one needs double brackets, and this one needs no brackets, right? Now, 1 pair of brackets is correct, because this is an additional layer, right? It's an additional array. So instead of just these brackets, yeah, who knows? Anyway, stupid garbage, no one cares. Going back to H8 sphere, all that means is that if that is in fact the only problem, we just need to spam brackets in here for no friggin' reason. So inside our v34 here, I just have to put an additional bracket set around this, I think, for no reason. I believe that is what we learned, but who knows? All right, so in here, I'm going to run this again to generate a different version of this file. I'm going to kill this buffer and let it load the new one in, and we'll see if it thinks that's fine, right? It didn't look like it even loaded that one in. So looking at this, now we've got this magical extra one here, right? And of course, I don't know how many more friggin' extra brackets it's going to want us to put into this nonsense. Because if that needed extra brackets, then everything probably needs extra brackets at some level, would be my suspicion. But I don't actually know. But it looks like it's still complaining about too many initializers. It's complaining now on the v3-4x. And I'm not sure. I want to go ahead and just, again, clip this out. I'm going to try and work this one backwards now to see if I can get rid of the error in here and then know exactly how many more ridiculous pairs of brackets for no reason I have to add. All right, so in here, by the way, all this is absolutely absurd that the programmer has to do this at all. It's absolutely ridiculous. Data specking in C is absolute garbage, and it only gets worse in C++. So anyway, that aside, if we compile this, which is the minimal set, now we just add brackets till this works, I guess. Such a piece of garbage. Just total freaking garbage. There we go. All right. There's our generate sphere. Here's me running it. I need this to reload. Did I put that in the right place? It's the triples. Yeah. And so we're probably going to have to double even more of those now. Actually, you know what? Let me save this one. And let me actually make multiple of each of them now, because we're probably going to have to double the outer ones too. Too many. So I'm tempted to just say that this entire thing is stupid and I don't want to deal with it. So I'm guessing that rather than try to make C++ actually do something right at all here, maybe I should just flatten these things down. Because this is ridiculous. How just take the things and put them in the freaking... It's just an array of numbers. What is wrong with you? It's so dumb. It can't even report where it thinks the error is, and it doesn't need any of these brackets. It should just take the data. Absolutely absurd. Anyway. All right, so now it thinks that this is a problem. Suddenly, who knows why, right? Just magical, the unicorn shat in the wrong place today. There we go. Yeah, and it can't seem to figure out what goes on there. I'm just wondering if, like, we just need every pair of brackets to be doubled or something like this. I really just have no idea what it's thinking. None whatsoever. So let's see. How could I define this? Let's suppose that we need to do this differently. Let's suppose that C++ is just so broken that you just don't even bother, right? What would we do? Well, we need two tables. We need tables of weights, and we need tables of sample directions, right? And so if we wanted to do that, really, we could just not define this, and we could just say that we were pointing to it, because we know that the data layout would be the same. It's just a large array of F32s, right? So in theory, if I make sure that the alignment is correct, I should be able to just dump a giant array of floats instead. And then C++ could try to get its head out of its anus, and we could actually program instead of handling this stupid compiler all day long. So, in order to do that, all we would really need to do is just this, right? Here's our light sampling sphere table. Guess what? It's a giant array of floats because that's the best Bjarne Stroustrup's ugly stepchild can do. And so when we come through here, I'm just going to dump them all out, right? I'm just going to dump float after float after float, and I'm just going to dump them in the order that I know that they should be, right? So there's all of the floats for this. No more of that. Here's all the floats for this. And then we close it off. So that produces the same layout that we want, right? It gives us what we actually needed. Like so. Of course, I have to actually run it. And now what you can see is, lo and behold, the C compiler was able to actually do its job for a change. What a shock. Hi, C compiler, thanks for coming to work today. And then if I go load up that file, we now see it's just a giant dump of floats, which, you know, is about all that it can handle, right? I'd like to put an intern on that. So I think inside H8 sphere, I'm going to add, I think we have a thing called global we can just put in there. So when we grab that light sampling sphere table, what I'd like to do is also align it. I don't know if we actually have in our platform code a way to specifically align things. I'm going to look. We don't really have a decal spec align, and we kind of need one in this particular case, because without a decal spec align, I don't think it's going to know what's going on. I'll try to putting that in just to give you some perspective on that. The reason is because we don't know what the compiler is going to do as far as loads. We don't know if it's going to try and use aligned loads. I don't need it to do that because unaligned loads are just fine for our purposes. But just in case, I need to put one of these into the declaration of the variable to make sure that they're aligned to a 16-byte boundary so that aligned loads, SIMD loads, won't fault. So I just need this to get that alignment specifier placed in there. And, you know, that would look something like this. Right? And now what I can do is actually just print out some ridiculous nonsense here as well and say, okay, after you've defined the table, we can just make this thing point to this other thing, right? So all I'm going to do is make it so it outputs the table as this giant floating point array of garbage, and then I'm just going to straight up cast it. And that's going to be the end of it. What a waste of time. Such a garbage language. All right. So now I'm going to go ahead and generate our file again. I'm going to compile. And I think we should now be working okay, but we'll see. Oops, put that inside. That actually has to go outside. And in theory now, that should allow us to effectively we're just defining it as a giant array of floats, but then we're using it as if it was an actual lighting sphere table, right? So we have to get that cast working properly. What's the problem here? Initializing handmade lighting 16. What? Did I forget a... I did. Just forgot a semicolon. All right. So now, hopefully we're good to go. Nope, not quite. Ah. That should be like that. We just want a pointer now. All right. So that took way longer than it should have because we thought temporarily that C++ might do something smart someday, but it doesn't, so why bother? I should have just done the float table to begin with because we know that would work. So now I think we're good to go. I think we have our pipeline flowing, and tomorrow we can concentrate on actually creating some useful values in our table. For now, we want to see if we can get anything here printing out, drawing spheres, sampling spheres. And what you can see there is we've got a sampling sphere exactly as we wanted. There's our points around the sphere. And what I'd like to do just really quickly before going to the Q&A, where hopefully all of the questions are, why does C++ suck so badly? And my answer will be because it requires people who know what they're doing to make a language that works. I'm going to go ahead and draw all of them. So all of the spheres that we actually created, I'm going to draw them all like on top of each other, right? I'm going to also kill this buffer. So in here where we loop over, I'm just going to do it over all the spheres. Like that. And so here, where we were just using the first one, I'm going to do all of them. And the other thing I'm going to do is I'm going to look at our color table. And I'm going to get a debug color off of the sphere. So we can, in the future, like right now, we don't expect to see anything interesting here. But in the future, what we'd like to see is those colors themselves are equally distributed, sort of. So we kind of want to see that our spheres have that nice property to them as well, right? So there's our sphere, and that's exactly what we wanted. I'm going to lift that up off the ground a little bit because it's a little hard for me to see the whole sphere. Remember, we were using a hemisphere beforehand, and now we're actually sampling an entire sphere. So what is that? Don't know what's going on there. Hold on one quick second. There we go. But I think we're all done with the sort of annoying plumbing part of things now. So we really just have to focus on creating a nice distribution now, but there we go, right? So there's our sampling, and you can see it's not very well distributed right now, right? You can actually see that. I may want that to be even higher up, honestly. Just to get it out of the way. So there's our sphere, right? Kind of floating up in the middle of nowhere. You can see it's got some big holes in it, right? And again, it's going to undersample because it's white noise on a cube projected onto a sphere, right? So that's our job for tomorrow. I'm going to go ahead and go to a Q&A now. Have you considered using Julia language to do any sort of game development? I've never even heard of Julia language. Uplink coder. I'm surprised the cast works as an initializer. Why are you surprised? You can always cast a pointer to anything to a pointer to anything else. Because all you're doing is just telling it to reinterpret the pointer, but the value stays the same, so the compiler's just like, okay, it's the same value, right? Just copies it copies one 8-byte value to another 8-byte value. That's it. So it doesn't actually do anything. It's not actually converting anything in an initializer. It's not looking at the data at all. You know what I'm saying to you? It's just copying the pointer. In this case, it's not even copying the pointer because it's just a hard-coded number where the array is. So it's just saying, hey, off you go. Why does C++ suck so badly? Good question. I don't know. I don't know how they are so bad at so many things. I don't know. It's like in order to contribute to the C++ language spec, you had to pass some kind of like, decathlon of stupidity, where you have to prove that you're stupid along many axes so that you won't accidentally do something right. Martins was asking if we can use C++ 11 align as. Yeah, if that's well enough supported, and you would know better than I, Martins, because you, I feel like, do a lot more platform work than I do these days. But if you think that's okay, I'm totally fine with it. So you're basically saying that in here, instead of a decal spec align, you want this. Just making sure I'm understanding the request right. Just waiting for Martins to confirm that's what he wanted me to do. What advice would you give to Bjarne Strustrup? Take real world programming more seriously, right? Programming is not a theoretical exercise. You know? It's like plumbing or something. Like, it actually has to move the water around the pipes. Like, you can't just theorize what might be nice and then not look at what the actual practical consequences of people trying to do actual work, you know, are. And like C++ with its ridiculous set of undefined behaviors and its like hamstrung feature set that always seems to have something wrong with it, it's just such garbage. If you're to make this a more 3D game, how would you go about modifying the renderer to support submissions of these? Would you keep the single vertex buffer setup? No. If you're trying to push like large 3D models down a pipeline, what you typically need to do is, do you know how we've got the textures set up right now? You would set up one of those for the models as well. So you would basically have a parallel thing to our texture, like our texture cache system, right? You'd have a parallel thing to that for your models. And every time you needed to use a model that wasn't in the cache, you would try to load it into the 3D memory, the memory on the 3D card. And whenever you wanted to draw it, you would reference that. So you don't want to be like sending down all the vertices every frame. Like, that's not going to work. So you have to just treat them like you treat textures. They're basically just vertex textures, right? What happened for you to turn on C++ so harshly? Well, nothing happened to cause me to turn on C++ so harshly. I always rant about C++. Just stupid compiler being bad about just getting data in there. right? Okay, so looks like they want this before the type, although I don't know if it matters. So is this what we're talking about? You just want that. That's totally fine by me. Since we're asking off-topic questions, is SPIRV in the direction of getting programmable ISOs for graphics hardware, or am I incorrect? Thoughts on SPIRV in general? No, SPIRV is just an intermediate representation of shaders. It doesn't really have anything to do with programmable ISOs for GPUs. You can think of SPIRV sort of as like Clang IR, if you're familiar with that, or just generally when your compiler ingests code normally. So, I give it one of these C files and I say compile this. It doesn't just read the C file as text and then spit machine code out the back. It reads it in, it builds a bunch of intermediate, data structures that it uses to like analyze the code and think about what it should do. And then eventually it runs something after it's gone through transformations and munged around and all sorts of stuff. Eventually it will kick out some machine code. When we say a programmable ISO for graphics hardware, we're talking about a spec for that machine code. SPIRV is like the compiler internal structures. So SPIRV is saying, look, let the shader get compiled into an intermediate format, then we'll hand that to the graphics card, and the graphics card will actually generate something that maps it to its ISA. So it's really, SPIRV doesn't really have anything to do with getting graphics hardware more programmable from a direct programming standpoint. In fact, it's the opposite of that. It's an insulation layer that prevents you from actually programming the graphics hardware, right? What do you think about Rust? I've never used Rust. My only thoughts on it are from looking at the things that people talk about. It doesn't sound like a language that really has much of a clue about things I care about. It seems like yet another C++ to me, but I haven't used it yet, so maybe I would think it was great, but I can pretty much tell you right now I wouldn't. I would probably think it sucks. It's probably slightly better than C++ though, because most languages are. What happened to Sean McGrath? I don't know. Did something happen to Sean McGrath? August 30th. All right, there were some swears on there. I guess I should have put that on the stream. Sorry, kids. He had a post from today, or yesterday. So I'm not sure about what happened to him. Maybe you mean something specific, I don't know. Can you build an entire game in a data-oriented mindset? Well, I do, really. I'm a CS student and I want to learn about rigid body physics. It seems resources I find on the internet are very basic tutorials or advanced academic papers. Is there a resource I can use with a not as steep learning curve? There probably is. That's a good question. There probably is, but I don't know what it is. Light sampling sphere has no padding then. It shouldn't, but we can make sure. I mean, we'll look, right? But it shouldn't really have, I don't think. But we can double check, right? We don't know, like, we may have to do some padding on here. Let me just. So, in order to maintain this alignment, we need this stuff to multiply out, okay? And so when we do the total raise per sphere, that 18 times 6, that is probably not what we want, right? So we probably want to do here is we probably want to include, whatever gets us back to a 16-byte boundary, because I don't know that we actually are on one at that point. These obviously will always be, but these are not, and so that would be the only thing, right? So effectively, like, whatever it would take to bump us up properly to the next, like, aligned number is what we would want. And we want that either way, so, like, this may do it for us, and then the cast might also do it for us in both cases, but we need to put in the padding there either way. Like, either the compiler has to do it for us or we have to do it, and if we do it, we know that it would be good, right? So that alignment padding should probably be there, and while we're thinking about it, I should probably just put it in there. But I guess what we would want it to be is just whatever the next padded number is. So, like, I assume you would want this. Again, I don't really want any of this, but because I don't know if the compiler will generate aligned loads. Like, I don't want it to, but it might. I just am trying to be overly cautious, right? So in there, we need to pad it out to make it so that we'll always be loading off an aligned value for each light sampling sphere. And to do that, we know that this was aligned because each one of these is 4 floats, so it's 16 bytes each one of these is. Each one of these is not, right? And so what we want to do is we want to say, well, okay, we know there's this many, right? We know that's how many there are of the cube side sort of bundles. We know each one has 6 in it, right? And so that is going to produce some number that's not a multiple of 16 bytes. So what we need to do is find, like, the next multiple of 16 bytes that it is. So to do that, I can just round up, basically, and then truncate. So I should be able to just do, like, something like this. To basically say, give me however many of these, like, floats I would need to round up to 16 bytes. But in this case, since I'm adding, since I'm doing this in F32s, which I probably want to stick to, these are actually not, it's not 16, right? It's actually just going to be like 3 and not 3 kind of a thing. So I'm not sure which way we want to do that. For now, I think what I might do is say, let's just make this padding be actually in bytes, which seems maybe like that's more flexible. It's just easier to calculate, really. And so in here, we would just say, look, it's 4 times the total number of floats we have, rounded up and then truncated to the 16, right? So we could do that. That's one way to do it. Another way to do it is to do it in F32s, which, again, like I said, I think it's a little bit better, and we know we don't really need the flexibility. So here we would just add 3 and 3, and do it just in float. So I think that's what we would want. Oops, sorry, it's not total raise per sphere. It's it's that, I believe. I need like a revert function, which I don't have right now. Don't know why, but I don't. It's kind of an old build, but all right. So in theory, that would do it. That is not right at all. I'm just getting a little sleepy. All right. Oops. So I think that's what we want. For padding, to ensure that we're always going to be able to be on the correct line. And so in here, right, we get off of this member, we know we're aligned. We come into this member, we have light sampling total raise per sphere times 6, which is 6 times 4 times 18. Right? And so then we need to know how many would put us up to the next 64-byte boundary, and we're computing that as 3. So let's see if that's actually true. So if we look at cube side weight, it's going to be 4 times 18 times 6. That's the number of actual bytes. So we're saying that if we add 3, that doesn't look right to me at all. Did I actually do that math right? Yes, I did that math wrong. Don't program when you're done for the day. That's pretty much the rules here. So you can see what I did here is I computed like what the next bump would be, but that's not actually what we want to do for alignment. This is where we are going to be, right? And so what we actually want here is, I don't know why I was doing that at all. That was just kind of off in left field. This is the actual number that we've advanced so far. It's 4 times the ray bundle sphere times 6. We want to get up to the next value. So all we really need to do is look at what its low bytes are and figure out how far we have to go to get there, right? So it's really just 4 minus whatever that low value is, right? Because whatever those bottom 2 bits are, well, bottom 2 bits of this value because it's in multiples of 4 bytes. Whatever those bottom 2 bits are, we just want to get to the next even multiple of them, right? So I believe that's actually what we want, not the thing I wrote before, which was kind of out of left field. So here we should get, so in this case it said there was no unalignment there, right? Meaning it thought this was a multiple of 4, right? And so when it did the padding, again, it found that this value was 0. So if we actually want to not put padding in when we don't need to, we would have to do this. Oops, sorry. So essentially what we do is we say, look, where are we in terms of alignment? If we're already aligned, we don't need to do one of these. If we aren't, then we just need to give ourselves however much we would need. And so to answer the question, it looks like we magically just picked numbers where that worked. So we don't really need the padding, it would seem. Let's see if that's actually true, now that we kind of like I have my wits about me again temporarily. So if we do 4 times the sphere number, right, times 6, it's 432. We want to know whether that's a multiple of 4, right? Because, and it is. So we don't actually need the padding unless somebody sets this number to something else, right? So it's good that we put that in there. We do want to be able to check for that padding. But in this particular case, we don't actually need it, right? Yeah. So if we look at those sampling spheres, you can see that it doesn't have the padding in there now. Does that make sense? But you're right, it would need that there. Oliver the Best Cat says, the one thing Rust has that makes it better than C++, no header files, that's enough right there. Again, it's not, though. Like, I'm not going to go through the trouble of switching everything I do over to another programming language just for no header files. You know, that's just not enough of a win. It's good, and you obviously would want that in any new language because header files are absurd. But, you know, it's not enough. You would need a significantly greater, you know, efficiency boost than that. So. And WobbleDuff asks, that learning curve seems to be the case with most complicated programming topics. This is referring back to the rigid body stuff, I think. How did you learn these topics when you started out? Slowly, and just by reading a lot and practicing, like doing stuff myself, you know. Rigid body dynamics is pretty bad. When I learned it, it was way worse because there were nobody had done physics game engines at all, pretty much. Looking Glass was one of the only people that really did anything serious in that direction. So it was really bad. You had to like basically learn it out of mechanics textbooks that weren't written in a computational mindset at all. Nowadays, a lot of that stuff's a lot easier because you can at least go look at papers that just are like, oh, hey, here's how we implement our rigid body dynamics. You can also go look at like public domain physics libraries even and just see what they do, right? So there's a lot more resources now, but I admit it's always a little hard. Right? It's always a case that when you're learning something new, it's hard to like put yourself in the right mindset, and it's hard to like know what it is you don't know, you know, and you got to muddle your way through it and kind of like just work on getting small individual pieces at a time, right? So. All right. Thanks everyone for joining me for those that are Handmade Hero. It's been a pleasure coding with you as always. It has not been a pleasure coding with Bjarne Strawstrip and the C++ gang, but then again, it never is. What can you do? I will be back here tomorrow when we'll work on our distribution of our points on the sphere, which is all we really need in order for us to be happy campers with our sphere INL file, which we can then use for lighting sampling with some relative certainty that it's doing a good job covering the samples that we actually need. that's it for today. I'll be back here tomorrow. Hope to see you back here for that. Till then, obviously, if you want to follow along the source code at home, you can always pre-order the game on handmadehero.org, and it comes with the source code, so if you want to play around with it, check that out. I will be back here tomorrow. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.